if you don't remember our discussion of motional EMF, let's start with just a brief reminder that first I'm going to need a magnetic field. No way of getting around the idea that you're going to have something that already has a magnetic field. And as we discovered yesterday in dealing with our can't even talk today, our solenoids, we know that electrical current will generate a magnetic field. Now, before you get too creative here, we're trying to produce electrical current. It's unlikely the electrical current we produce could be then used to make a magnetic field that would then be turned around to produce electrical current. Before you start thinking that we have like some kind of perpetual motion machine here, you do realize that that's never going to happen. It violates the rules of physics. Now, you guys are smart, you're sharp, you don't have to believe me, but there are rules that I will not explain to you because they're outside the boundaries of this course that will limit this, but we will be able to demonstrate why the current we produce can't be used to generate the magnetic field to produce our current. There are things in place to prevent that. And when I say things in place, I said it like, we created structures. No, there are just rules in physics. Conservation of energy is a rule that just doesn't get violated. It seems to be the law that governs the universe. So we can't create energy out of nothing. So although we're going to take a look at Faraday's law, there's another very important law that we're going to learn in tandem called Lenz's law. And Lenz's law really does provide us a little more background as to what's happening with Faraday's law and why we don't get something for nothing. Now, if you remember back to when we were talking about motional EMF, this was last week or early this week, in order to generate that, we needed a conductor. And we were going to take that conductor and forcibly drag it through a magnetic field. Meaning we're going to give it some velocity, likely by applying a force to it. When we did so, we just talked about the fact that positively charged particles in the wire would experience a force. By the way, if there's a positively charged particle in this bar, and the bar is being dragged through the magnetic field, could you use your right-hand rule real quick to tell me what direction the force on the positive particle would be? I know I'm hammering home right-hand rule, but I still have, out of my 26 students here, a subset that can't tell me the answer to this. So I want to make sure we're all good. Everybody have my answer? Are we sure? Julie, what direction would a positively charged particle be pushed? That's right. So positive particles would accumulate at the top. Now, we know that's not exactly what happens. Can you take just a moment to prove to yourself that negative particles would be pushed downwards? You could use the left-hand rule for this, or just do the right-hand rule again and note that it's going to go in the other direction. So we will get negative particles towards the bottom. This proof is fast, so I don't want to spend a lot of time in it. This is going to create an electric field inside the bar. This electric field will continue to increase until the net force on the particles is zero, which means this will continue until QE equals QVB. This V, by the way, is the velocity of the bar through the field. Now, if our bar were, say, L long, and if I remember correctly, that electric potential equals electric field times distance, then I could cross out those Q's and put EMF over L equals VB, or my motional EMF equals BLV. Did that about a week ago. Motional EMF. Now, I don't care. Power equals voltage, BLV, times current, which is BLV over R, which means the power dissipation in the bulb is B squared, L squared, V squared over the resistance. Okay so far? I just combined some things together. Now, how much force does it take to push this bar into the magnetic field? We don't get something for nothing. The bar just can't be drifting into the magnetic field and I get light. You saw what I had to do. I had to crank that thing to get the light to come on. What you guys couldn't tell is that there was a lot of resistance to me turning that crank. Part of it's friction. Part of it didn't exist until the motor began to spin. Because the instant this bar enters the magnetic field, a current is being generated in this direction. What is the size of the force created by this current? I'll tell you the force is in that way, right-hand rule. The current is up, the magnetic field is into the board, so the moment I connect this circuit, and the moment it begins to go into the magnetic field, there's a force created to keep it out of the magnetic field, to try and prevent it from going into the magnetic field. And that force has to be equal to ILB. Sorry. It's the whole length of the wire. So this current that I just created also prevents the bar from going into the magnetic field, which means I will have to pull on the bar with at least an equal-sized force just for the bar to travel at a constant velocity into the magnetic field. Now, I calculated the power using voltage times current to demonstrate how much power I would get from my system if the bar moved into the field at a velocity v. And when I was done, I got B squared, L squared, V squared over R. And then I receive a watt of electrical power in the circuit. But the bar doesn't go into the magnetic field on its own. If you want the bar into the magnetic field, you will have to lose energy in order for the electrical system to gain energy. You have to do work on the bar. You don't get something for nothing. So a bar you can't just like throw this thing at a magnetic field and think that it will go into the magnetic field on its own. The moment it hits the magnetic field, it's going to feel resistance. Guys, you did this at Busch Gardens, right? The eddy current demonstration with the pendulum that had to hit the magnetic field and suddenly stop. That force that stopped it is this force. The generation of a current that caused a force due to the magnetic field. That's what happened. As the bar goes in, we generated a current. The generation of that current immediately tries to prevent the bar from going in. Now, a couple things to point out. If this wire isn't here, that force isn't required. The bar can move through the magnetic field, create an EMF, and that doesn't cost you anything. It's only when you attempt to use that EMF to create electrical power do you suddenly generate a current which then tries to stop the bar. Now that's not the only limit, that's the first limit. Faraday's law has some interesting consequence. Let's consider the moment the bar is just about to bring the bulb into the magnetic field. So I'm applying my force, the bar is moving this way. My light bulb is lit up, I have current in this direction. One more instant later, both sides of the bar, the entire loop is in the magnetic field. You guys follow me? Got the entire loop in the magnetic field. We have a problem. There's a current everywhere in this loop. Current this way, use red. Current this way, current this way, a current this way, and a current this way. Which means there's a force actually on all four wires. Now, the force in the top and bottom wire, I hope you guys can use your right-hand rule to figure out what the direction of that force is on the top and bottom wire. So you found the force on the top and bottom wire, something like that. We already know there's a force on this wire this way. The moment this other wire gets in there, what's the direction of the force on it? Do we all agree that the force in that wire has to be this way? So the moment the entire loop is in the magnetic field, the net force instantaneously becomes zero. Which means I get it all in there and then it just goes by itself. Seems awesome until you realize what's going to happen to the charged particles in both wires. Think for just a moment. We know that the charged particle, the positive particle on the right-hand bar, in this bar right here, that charged particle has to experience an upward force due to the magnetic field. What direction will this particle experience a force? Just the particle, not the wire. Do you realize it has to be up as well? I mean, all the charges in here are experiencing an upward force. But the fact that the two opposing wires both experience an upward force means that the moment the entire loop is in the magnetic field, the current instantaneously stops. There is no EMF. The EMF disappears immediately the moment the entire loop is in the magnetic field. That's because the charged particles in the wire are being pushed against each other now. When the one wire was trailing outside the magnetic field, it wasn't having any effect on the individual charges in the wire, so they could be pushed around. But the moment both parts of that loop go into the magnetic field, that's no longer the case. Both EMFs immediately go away. That's why the moment you get it in there, you don't have to keep pushing it because there's no current being generated any longer. The bulb goes out the moment the whole thing is in the magnetic field. Now, eventually, you realize that side of the bar is going to make it to the end of the magnetic field. Which means the side with the light bulb suddenly is the one that's going to be generating the energy. If you don't understand what I'm about to say, positive particle right here, it's still moving to the right in the magnetic field. It must experience a force upwards. But a positive particle here is no longer in a magnetic field. It experiences no force from the magnetic field, which means the moment I start to pull this loop out of the magnetic field, a current is suddenly created because an EMF is created over here. But this new EMF causes a current that's in the opposite direction as before. So now the particles are being pushed clockwise, when before they were being pushed counterclockwise. The crux is this, and I want you to write this down since we're at the end. Faraday's law uses motional EMF, but it's really about flux. Faraday's law is about a change in magnetic flux. An EMF is only produced when the magnetic flux is changing. All right. I know you don't remember this, but power in mechanics. And I'm just doing this for Owen's benefit. Owen, do you remember how to calculate power in mechanics? Work over time, sure. Can you tell me what work is? Yeah, just simpler. If I wanted to calculate work, like using algebra. Force times distance over time. What's distance over time? Thank you. Just wanted to make sure we brushed up on it all. Power required by me using mechanics to get this thing in there is going to be ILB times the velocity. However, I is BLV over R times LBV, which is going to be B squared, L squared, V squared over R. I don't know if you see the implications, but he asked Owen to help me figure out how much power I would have to exert on the bar in order to push it into the magnetic field at velocity V. And it would be related to the force I would have to apply. And using that derivation, I'm showing you very clearly that for every watt of power you expend,